Welcome to another edition of Community Conversations with the MemSQL community. I'm Dominic Ravita, Field CTO, and it's a pleasure to be joined by Jay Srinivasan of Infiswift Technologies. Welcome, Jay.
Thank you, Dominic. Happy to be here.
Great to have you. So let's get started. So we're going to cover Infiswift Technologies, what you guys are doing in the IoT and AI space. Before we get into those topics, I think the audience would be interested in your background. So let's start out a little bit with what's the first program you developed, and to tell us the story there.
Sure. My first program was done at my high school, where I wrote a program to find the day of the week that your birthday fell on. So I enter your date of birth, and then it'll tell you the day of the week your birthday was on. It was the first program in my school, like of that kind of a complexity that we wrote when we first learned basic programming. And it was a big hit, and would show it to other friends, and they would type, and then they would be amazed to find that. Basically, it was based on the observation that whenever a day starts, the first day of the year is the same day the year ends. And then so the next year would start one day later. So, and then you would have to adjust for the leap year calculations when you go back and forth. So it was based on that observation, and then codified it for 1 year, and then you can go back any number of years and then using that calculation. So that was like pretty inspiring to me that, I could do something that would take a lot of calculations and then put it in a program and then have it really do something amazing. That's how my interest in computer science really started. And then I went on to graduate school, both in India for my bachelor's degree, as well as for my master's degree in University of Iowa in US.
Great. With that first project, did you what tools did you use, and did you share the program for others to install, or how did you?
So yeah, we had very limited computer facilities at the time. It was like a shared computer that we all use for certain times of the class. So we would have to put the program and then bring it with us in our floppy disks, and then I would install and show it to people during the class hours, and then later whenever we needed, I would just install it and show it. It was run in GW Basic on a 386 PC at the time.
Great, fun. SneakerNet with disks, right?
Yeah.
So you did your undergrad and went to graduate school at University of Iowa in computer science, and then you worked at Microsoft. Tell us about your time at Microsoft and some interesting projects you were involved in.
Sure. In Microsoft, I was for 12 years, mostly around networking, kind of networking and distributed systems was my specialty. So first 5 years I was in Windows networking, and next 5 years I was in Microsoft Office, working on live meeting and different technologies around that. And then last couple of years was on Microsoft Azure. Back then it was called Windows Azure. So I was in that team, and our team developed Microsoft's first software load balancer that powers Microsoft Azure even today. So we developed the core platform for the software-based load balancer. Prior to that, we were using hardware load balancers for Azure. So our team deployed the first software load balancer. So very proud of that work.
Terrific. So that code still is in use today. I'm sure
Yes.
Getting a lot of exercise as Azure.
Yes.
And yeah, you mentioned that Azure at the time was called Windows Azure. Why is it not called Windows Azure today? Tell us that story.
Yeah, I think at that time it was Steve Ballmer's era. So when it came to naming, when the discussion came to naming Azure, so Steve was reportedly told that the first name has to be Windows, and then followed by another name. So that kind of reflected the company culture at that time to promote Windows primarily. But later on, as we see from the history, the focus is on being more open and being more embracing, and then name naturally changed to Microsoft Azure to reflect the broader suite of technologies you can bring to run on the Azure workloads.
Right. The observation that the cloud is not about the operating system.
Right.
And then you left Microsoft to go work on an operating system. Tell us about that.
Yes. From Microsoft, I went to Google. So I worked on Chrome operating system. So I developed the auto update feature that updates all the Chromebooks for every release, almost like every 6 weeks, I believe. Then I worked on Google Fiber product, and then I worked on Android. We developed a new product for the next billion users in the emerging markets. So developing the backend and distributed systems to power that SaaS service. Yeah, it was a lot of fun work.
Terrific. And that led you to join Infiswift and start your own team and create your own platform. Tell the audience a little bit about what Infiswift Technologies does.
Sure. Yes. After 5 years at Google, I left to join Infiswift as the first engineer. So essentially, the promise of IoT was and still is huge, with not a lot of adoption happening as much as projected and as much as there is potential. So one of the core foundation of Infiswift was to build a IoT platform that is really scalable, and by developing it with really cutting edge smart technologies that power many of these services at Google and Microsoft in terms of being able to scale with really low cost hardware. We wanted to bring that same technology to this IoT platform to make it really scale well for lots of sensor data and to be cost effective at the same time. So that required essentially rethinking the IoT platform to have that capabilities by design so that it's cost effective. And we started with building that IoT platform, and first couple of years we spent on building the world's fastest MQTT broker, which is the heart of the IoT platform. So our broker serves traffic at just 108 microsecond latency between the pub and sub within the network within our platform. So that's really amazingly fast, and we didn't have that kind of a product. That's why we ended up developing our own homegrown broker. We have a couple of patents on that as well, on some of the technologies that has gone into it. So we started with the IoT fabric, and then last couple of years we realized that we could do a lot more, not just ingest the data and store it, but also analyze it and provide the insights that customers are looking for from the data. So that has been a really fruitful journey with us developing AI fabric on top of our IoT platform with ready-made algorithms and capabilities to solve a variety of problems, especially around optimization, around machine vision, around digitization, around asset tracking, and like integrating with SCADA systems. A lot of industrial focused technology areas, which are kind of repeated themes we see in many industry space. So why start from scratch building all that solution? So we built what we call as Infiswift IoT and AI fabric, which is the heart of our company, this product, which we use to develop different applications for different customers. And that's been a very fruitful journey.
So let's talk a little bit about what MQTT is and how it is you built that product, and maybe a little bit about the development journey.
Sure. So the MQTT stands for a Message Queue Telemetry Transport. It's a 20-year-old protocol. Recently became popular with IoT adoption. Unlike HTTP, which is a request response protocol, MQTT is a publish subscribe protocol. and it's ideally suited for devices because the overhead is really low, especially for IoT sensor devices that run on coin cell batteries and really low power mode. So the MQTT protocol lends itself to that kind of devices because the responsibilities of the device is so low. It just has to publish a heartbeat or a particular sensor data every once in a while, and you don't need a fancy HTTP stack with all the options and different ways of doing. HTTP is mainly meant, it was mainly meant for web applications, whereas MQTT is mainly meant for, like, you can say, headless devices which exchange data with some other party or with each other. So that's where the pubsub becomes interesting, because a device could just publish its own status about, let's say, temperature or its state, not worry about who is consuming and not having to talk to every consumer. So rather, the MQTT broker is the one that's coordinating all those transactions so that the device's footprint become really small. So they just have to care about distributing it to a broker, and then the broker is responsible for distributing it to all other subscribers. So it makes it agnostic and provides a lot of value where subscribers could come in and go, and the publishing is asynchronously done. So there's no need for both of them to be together at the same time. That's one of the biggest benefits of MQTT.
Mm-hmm. And what do you think has driven the popularity and adoption of MQTT in recent years?
Yes, it's mainly the low footprint of the stack itself. It's a very thin layer on top of TCP stack. The spec is really small, so you could implement an MQTT client pretty easily. And mainly the efficiency. And there have been studies showing how it's much more efficient than HTTP in terms of conserving the bandwidth and in terms of requiring low power to run on the client stack.
So the sorts of application use cases that Infiswift customers use it for are in solar, renewables, energy, oil and gas, logistics. Give us some examples of how Infiswift is used, and a little bit about how that your platform plugs into other services and applications.
Sure. So we get a lot of data from photovoltaic panels and inverters, combiners, meters, this kind of equipment in the field. So sometimes they are IoT enabled and sometimes they are not. So we have different mechanisms by which to ingest the data from these sources. If they are directly IoT enabled, typically they implement MQTT protocol, and then we configure them with our broker endpoint, and then they directly publish the data to us. In some cases where they are legacy devices that support Modbus TCP or Modbus RTU and those kind of protocols, we have a gateway, IoT capable gateway in front of them, and then the gateway interfaces with those legacy devices and then transmits the payload to us in terms of MQTT. So that's how we integrate with that data from these different sources. That's one of the ways we use MQTT. And then the applications on the other side that are consuming this data, they are asynchronously running on their own, either they are real-time or they are historical data. They can feed off of both. And then they subscribe to the data, and then they do whatever they want with that. Typically, we do a lot of forecasting, optimization, understanding, and providing analytics so that the user can see what the patterns are, and also do anomaly detection. And we also use all the data for like doing supervised learning and unsupervised learning as different applications need. Yeah, we do a lot with the data as well.
So what does it look like from the point of the IoT sensor data through your platform? How does that data go from the sensor through the platform and back for your customers?
Yes, so from the sensors, as I said, it either goes through a private protocol and then gets converted to MQTT at the gateway, or it originates directly as MQTT in the sensor device itself, depending on what the sensor is capable of. And then the next step is coming to the broker, and then from the broker it goes to the applications, and then the applications are typically backend applications or mobile applications that consume the real-time data. For example, if it were an asset tracking kind of application, then like they say that the farm vehicles would have our client, and then they would publish MQTT via GSM connection from the mobile phones, from the farm equipment. That's the hardware we used. And then on the server, we would collect it, and then the farm managers would have a mobile app with MQTT client running with real-time location data received from all the trucks from over hundreds of miles of their farms. So physically they can't be there all at the same place. So, but just sitting in their couch, they can just watch the real-time performance of all the vehicles, whether the right vehicles are there at the right place where they need to be. If not, just call up that particular driver or that particular operator and ask what's going on. So for these kind of communications, MQTT lends itself really well. And also we as an Infiswift have developed a layer on top of MQTT, which is to provide integrate it with the historical data archival, because MQTT supports only real-time mode by itself. So we need a separate mechanism to archive all the historical data from the MQTT streams. So we have our own concept of a stream, which is tightly coupled with the MQTT publish. So that way the client doesn't have to do anything apart from publishing the MQTT payload. And then we internally archive it to streams, so that applications that require nightly runs or analytics applications that require that they don't typically operate in real time, they operate in batch mode with a cron job and a daily or retraining for machine learning applications. All those run off of this historical data that's getting collected every day basis. So our main innovation in the MQTT area is to combine these two in a way that you don't need to do any additional work or configuration. And also another important thing is security. Because when you have these devices all floating around in the field, you don't want any MQTT device to have more access than what it should. MQTT in the protocol itself doesn't have any topic level security. It only has a connection level security. You can give a username, password to authenticate. That's about it. Whereas that's not enough for us, because if you get one, if you manage to hack one particular equipment's credentials and then get those credentials, now you could, with a wildcard filter, you could subscribe to any topic you want, right? So that wouldn't work for us. So we needed to provide really fine-grained security. So we have in our stack the ability to say user A has access to this one data point of this one stream of this particular device. We can specify to that granularity and nothing more than that. And similarly for backend applications which need all the data from all the devices, we could also configure it as widely as, okay, everything from this account, it's okay to send it to this backend application because they're running in a trusted cloud environment. So like that, our main innovation is to take this and then make it uniform for both real-time and historical, so that you don't need to deal with two different access control mechanisms when it comes to controlling who can subscribe to what data versus who can access what historical data, because they need to be in sync. Otherwise, your security model, if you anytime you say do the same thing in two different things, it's bound to fail. So we wanted to solve that problem in a fundamental way through integration with our stack. And that's one of the very unique value proposition in our offering of the MQTT and our IoT platform.
Terrific.
Then we not only provide to separate access within the customer, because many times our customers are actually themselves platform companies which are building platforms for their customers. For example, one of our major customers, for one of our major customers, we are building an energy platform. So which means they'll have their own customer intent. So we can't stop protecting one customer from another customer. We also need to protect the data of customer from the other customers. So it's a multi-level hierarchical security model we have implemented on top of MQTT, and that's integrate with the stack, so you don't, once you just get your client ID and your credentials, everything is configured for you in a very secure manner, and only administrators can change that security. So even if one credential is lost or stolen, that device, with that credentials, you cannot do much more than just send some garbage data to the broker, and then we can invalidate those credentials when we see those patterns.
Mm-hmm.
So we have really taken that security very seriously, and that's one of the core values we have.
That's terrific. Yeah, security is really important in this area. There was a popular breach that was advertised or circulated a lot several years ago where gas pumps had been hacked. MQTT seemed to be at fault with a breached password. So yeah, as more of these IoT sensors are out there in the wild, a simple password protection is clearly not enough for that use case.
Right.
So you mentioned that you Infiswift and this capability is provided a couple different ways. It sounds like you were talking about API level integration, but also it can be included in platforms of platforms.
Right.
And so it sounds like your design and goals right up front weren't targeted at a particular cloud platform to build using their building blocks. You needed more flexibility to deploy in maybe several different public cloud environments, but also other sorts of data center environments. So, on that front, when you talk about your design goals, tell us about how you design the system such that it had these flexible deployment options for cloud, on-prem, hybrid, et cetera.
Sure. Yes. So when we started out building our IoT platform, we were clear that we are actually targeting industrial customers with large-scale installations, because that's where they need the scale and the latency that we are particularly focusing on. So one of the things we learned early on is that people are going to have different cloud tie-ups already, and we are not going to have them change it for embracing IoT or the AI layer. So we wanted to make sure we go where their data is, not necessarily having to force them to bring their data to us. So because of that, we made every component that's part of the platform really self-contained, and also not take any dependency on any particular cloud's native capabilities. Because of that, our entire platform is portable, which means you can run your application, you can write your application for our platform once, and then later on, your decision to change cloud changes because one provider is offering much cheaper prices due to competition with others. Then you are not at the mercy of one particular provider. Then you can switch over easily when you know that your applications are not going to be bound. So essentially, we use a cloud only for running our workloads, but the entire stack is built from ground up with both our own homegrown components, especially for the core platform features, as well as we embrace open source tools where we don't have to worry, we don't have to reinvent the wheel. We take those for faster development and then bundle it as part of our platform and provide an integrated API and mechanisms to deal with the whole stack in a holistic manner. And that's one of the reasons actually why we were interested in MemSQL, because of the MemSQL's ability to be completely hostable on-prem. For us, it was not just a matter of even moving across clouds, but it's also one of the most important requirement is to be able to deploy it completely on-prem. So that so choices like MemSQL are an example of how we built the stack to be completely self-contained and hostable anywhere we want.
Mm-hmm. Right. And you mentioned talking about data management in MemSQL. You mentioned earlier that your platform has the ability to combine real-time data along with historical data.
Right.
You discussed that in terms of the MQTT broker. What does it mean for the transactional processing and the analytic processing that you provide? And when you started to look for, you started building this platform, I believe, roughly 5 or 6 years ago. When you started to spec out and identify your requirements, Tell us about that intent to support transactions and analytics, and what you sort of started out as your key. I think you identified 4 key requirements up front for the data management tier.
Right. So, yeah, as I said, I joined as a first engineer, so I had the full choice to make the technology decision for our IoT platform. And we were starting from scratch, so we didn't have any legacy stack to deal with. And so one of the key things we wanted to make sure is, even though kind of NoSQL was gaining a lot of popularity towards the end of my stint at Google, the whole Google was moving to Spanner, which is actually a SQL-based interface. Of course, it's done in a very scalable manner, so which shows that actually you can use SQL and still be scalable. So you don't have to necessarily go to NoSQL for and sacrifice all the transaction capabilities and the wonderful tools that are available with SQL-based interface just to scale. So that's been our primary conviction at that point, and we can see how that's actually turning out to be true with more and more capabilities being added to these SQL-based scalable, horizontally scalable products. So one of the primary things we were looking for is a SQL interface, and the second thing is we wanted to store lots of sensor data. Obviously, that will be a disk-based storage. But at the same time, we also wanted the platform to be as fast as it can for the real-time data distribution, which means we needed a kind of in-memory database. So that's something we are looking for. I mean, I didn't know that MemSQL as a product existed at that time, so I just had these requirements written down, and then was just Googling for things that would satisfy our needs. So of course, Spanner wasn't publicly available at that time. It was still only within Google. But even if it was generally available, it wouldn't have been my first choice because it had everything we wanted, but it was not having a hostable on-prem capability, which was a big deal for us. So then, MemSQL came as the top choice for providing all this that we wanted: the transaction support, the SQL interface, ability to store in-memory store and column store, and on-prem support. And also a couple of things that really surprised us was that MemSQL was not only providing a SQL interface, but it also had MySQL wire compatibility, which was really big deal for us because even now, when we do on-prem installations, sometimes they have only one server and they can't afford an entire MemSQL installation with aggregator and 2 leaf nodes. So in those cases, we say that's fine because our stack is written for MemSQL. It's implicitly MySQL compatible. So we just install a MySQL version for those on-prem scenarios where they can't afford a larger hardware footprint. And then our stack and all the applications on the platform works fine. So that was a big support. And then second thing is one of the reasons mainly people go to NoSQL is also the implicit JSON support, which was missing in SQL type products before. But with the MemSQL providing native first class support for JSON, so that also made it really convenient, because even though we use SQL, all our payloads are actually JSON payloads. So we could directly store, index on the JSON fields and then query on the JSON fields. That was something more than what we were looking for. So it was a perfect choice for us. And 4 years we've been using, we're quite happy with our choice.
Mm-hmm. Yeah, JSON payloads and IoT use cases go hand in hand.
Right.
Right. So breaking down each of those requirements, it might not be obvious to everyone listening, but why was a in-memory row store in your short list of requirements?
As I said, we wanted the platform to be as fast as possible for addressing some of the most demanding low latency scenarios. For example, one of the applications that we just completed It's called a virtual power plant. So we recently performed a scalability test for a virtual power plant to make sure that the broker and the platform can scale to such demands. So this is in the energy market where it's called a balancing market scenario, where the virtual power plant acts as a reserve power source for what they call a synchronized frequency restoration reserve. So in this use case, the aggregator system sends a command every 10 seconds to our platform, the energy platform or the VPP platform. And this has to be distributed to, in the test, we had like 100,000 batteries, each 10 kilowatt hour battery, each behind an IoT gateway device. So this was the demand of the test. So we were able to sustain the traffic for hours together with an average end-to-end round-trip latency of only 800 milliseconds for each command. So even though we had 10 seconds, we couldn't afford to use up all the 10 seconds for our own platform, because the devices we are talking to are slow devices like the gateway device and the batteries, and it has to go through the internet round trip. So we needed to keep the maximum time budget for all these inherent weak links in the pipeline. So that means our platform has to be extremely fast to meet these sensitive loads. Again, 10 seconds is just what we started with for the experiment, but in future it could get reduced even further to seconds and sub-seconds. So if we needed a platform that can support these high energy, high frequency transactions, we had to primarily store the data in memory for all the pubsub related thing. And also another thing is, even if we hadn't, if we didn't have a in-memory database, anyway, we would have to have a in-memory cache for solving it, right? So if you're going to anyway spend, like resources in putting up a Redis cache or another cache like that for your in-memory needs, why not just go with the in-memory database itself and reduce that caching layer and get the transaction support and keep a SQL interface, right? So we had the best of everything with the MemSQL design. So that's one example of how our platform is, the entire product is able to do a round trip of 800 milliseconds because of the in-memory store, as well as we were able to, just for the core platform itself, we took only 24 milliseconds to complete the round trip, all the platform level work. So the remaining 700 and whatever seconds was for the rest of the application, and the whole application also is using the MemSQL. That's another advantage. So you are using the same database for both the platform as well as applications in this case, rather than having to choose two different technologies. So that's why the row store is required for the real-time thing, and the column store is required for the storing all the time series data that we'll get from all these operations.
Okay, so that's a great explanation. You're using the in-memory row store to ingest high-speed sensor data at a very low, it sounds like in less than 24 milliseconds is the time spent in MemSQL in the row store there. And for workloads that are analytic in nature, you're storing that in the MemSQL column store. Is that right?
Right.
And so what are some of how are you serving these analytic workloads? Are these concurrent API reads, performing analytic type complex queries and joins, or are they also human users over web interfaces looking at real-time moving dashboards? All of the above? How would you characterize the analytic?
It's all the above. It's all the above. As I mentioned, we serve customers in oil and gas, solar, storage, asset tracking, manufacturing, right? So all these customers have quite different workloads and time of use and patterns, and besides that, we also do a lot of ML algorithms on the data to train our models, to retrain our models on a nightly basis. We do a lot of forecasting for PV generation, for demand forecasting, and all this require quite a, I could say, it's not like you can just tune it for one thing, because remember, we are building a platform, not a single application. So we had to choose a really scalable architecture that meets all that varying demands without us having to special case and fine tune every single query. So that's where MemSQL has been doing really good for us, because we have only one production cluster to serve all the clients from all these different verticals. So it's a mix of all of what you said. Yeah, some are web dashboards, some are API queries for internal calculations, backend processes, some are machine learning based analytics queries. Everything is done in the same roof.
And on average, how many concurrent connections to MemSQL do you have at any point in time?
So that we don't have a lot of concurrent connections because, as I said, a lot of them are based on the backend processing, but they do a lot of high volume of transactions. Because, for example, when a process does it queries a lots of data for like an entire day, we sometimes sample data at like 300 millisecond frequency for like the SCADA systems. Because for example, for our manufacturing application, we are trying to find bottlenecks in the entire manufacturing assembly pipeline. So you can know which component is waiting on what, and then in order to do those fine-grained calculations, we need to sample the data at which component is free or busy every 300 milliseconds, and then use that data to make the computation. So all that high frequency data is stored. So when you say, okay, let me do the analytics for the last hour, it's like tons of data that you get. So that's where we have a lot of those use cases. And in terms of the overall concurrent connection, probably I would say we will be peaking around like 1,000 connections overall, but a lot of them are like really high volume transactions.
You're doing a lot of work, asking the data to do a lot of lifting on aggregations, processing queries. So how many sensors are supported with this production environment that MemSQL is backing?
So currently, overall, we'll probably have like maybe it'll be in the range of like a couple of 100,000 with various equipment. Yeah.
And how much data is ingested, per second on average from the sensors?
It varies according to the application, as I said, since we provide a platform, right? So different applications have, so as I said, some manufacturing applications, we ingest 300 millisecond data. And in some cases, it's, 1 minute data, and then we downsample them and store them as 5-minute data. So we have different gradations of those time series data for different applications.
Mm-hmm. So but in aggregate on a daily basis, is it terabytes of data that's being ingested across all of the applications into the platform, or is it more on the gigabyte?
Yeah, it's more on the gigabytes at the point.
Gotcha. And tell us about the MemSQL cluster itself and how much data is under management currently.
Yes, so we are still under like 128 GB limit of the MemSQL for the free tier. So we run a 2-leaf cluster, 2-leaf node cluster. And the beauty is, even though we have ingested data like for a long time, we are still, because of the compression, we found that we are getting a 7x compression from the column store. So still our actual footprint on the data is very, very less, even though we have ingested tons of data for more than a year for some of the equipment, really high frequency data. Because of the compression and the column store, we have significant reduction in the actual storage. So that's one reason why we, even though we have so much data, we are still not exceeding the 128 GB limit.
Right. So you went looking for your initial requirements. You had 4 of them, and you were looking for an in-memory row store, a high-speed column store. You were looking for a solution that had a SQL interface.
Right.
And you were looking for something that could provide low latency, predictable queries. But it sounds like you also found other attributes such as MySQL wire protocol compatibility that aids with adoption.
Right.
And also you mentioned you had planned to, or you typically these systems might require a caching layer in front.
Right.
What did you find on that front as you started using MemSQL?
Yes, yeah, because MemSQL itself is an in-memory database, we didn't have to invest in a separate caching layer. We do have some cache in our own application for just within the application process itself, but that's just a small amount of cache. But we didn't have to use another Redis or other caching product on top of what we have. So that's a biggest advantage. And also one of the advantages that you were summarizing, I would add that it's also the fact that it's hostable on-prem.
Hostable on-prem. Okay.
Yeah. So that's a big advantage.
Terrific. So you mentioned that also you're doing some training models with machine learning and AI. Right. How is that incorporated? And what's the interplay between your model training? You mentioned that you retrain these models on a daily basis. You've operationalized them to put them in production. And how I have two questions there. One is sort of your MLOps workflow. And secondly, what role does MemSQL play in that, and how does it benefit that daily kind of cadence with MLOps?
Sure. Yeah. So we have MLOps for our the forecasting kind of applications. For example, for PV generation, we need to do a daily forecast. As I mentioned, for the virtual power plant, actually the virtual power plant is like you can think of it as the Uber for electricity, right? And some homes have more production, some homes have less production, so you need to kind of balance and even out the distribution so that you don't have to make capital investments on the grid to serve increasing energy demands of people. So that's where the virtual power plant, essentially what it does is it aggregates all the, you can say, unused capacities of batteries across the hundreds of thousands of homes, and then presents it as a single power source to the grid, so that the grid can rely on this particular, you can say, virtual power plant to say at any time, it say, okay, can you give me 2 megawatts now, or can you absorb 1 megawatt excess I have? So all this they call that flexibility. So that grid is looking for that flexibility, because you cannot ask that of a coal plant, because it takes a lot of time to start the plant before it can produce certain amount. Whereas with dischargeable batteries, at a moment's notice, we can just say, yes, I can give you 2 megawatt right now, without having to wait and have a plant that's like a thermal power plant or any other power plant start up and then shut down. So those operations are expensive. And whereas with the invention of batteries and using it with IoT, it gives a tremendous opportunities to really serve this energy market by providing this dispatchable energy, which can be just turned on and off anytime at a command's notice.
So would you call that more maybe dynamic demand response?
Yes, exactly. So yeah, dynamic demand response, so that the capital investments on the grid is lowered, and the battery owners get incentives in exchange for allowing the grid to use the unused capacity through this virtual power plant. So these are the kind of applications we are working on for our customers. So an aspect of that is the low latency with which we need to deliver. And I'm sorry, I forgot your original question.
Well, in your daily cadence for MLOps.
Yes. So this is where because at any point in time, we need to know how much this particular battery will have the capacity, how much capacity it has at the moment, and what will be its you can say state of charge, like 1 hour from now, 1 day, 2 hours from now, 1 day from now, so that you can plan how much capacity I have within my system, which is the virtual power plant. Because when we report to the grid, hey, I can give you this much capacity on a sustained basis every day, I better be sure that some battery or other has that capacity. It doesn't matter whether battery A has or battery B has. but aggregate capacity of the system under management should match what I'm promising to the grid of what I'm capable of as a power plant. So that means we need to constantly evaluate what is the charge and then how much we are projecting. So that's where the forecasts come into picture. So that means we should be constantly running these forecasting algorithms based on the latest data available, and then do the fine tuning in our learning to always be as accurate as we can with the reality. Because sometimes models are based on models, right? Like they may not match the reality, but we need to continuously fine tune them to the reality so that we can know what is ahead, and then be able to make that promise that we're making to the grid reality. So that's where we do a lot of those actual calculations of, because we may also have photovoltaic panels. So that means we need to forecast how much these panels will produce electricity, but that's going to depend on weather. That means we need to take the weather data into account and integrate the weather data. And then, so it requires a lot of ingestion of all these sources, and then constant computation, and then giving the results, and then providing a real-time control. So you can see how all these are coming together in these kind of applications.
So is the training phase, is that workload running directly against the same MemSQL cluster?
Yes.
Or
Yes, it's the same cluster. Yeah, that's the beauty. Otherwise, if it were just storing cheap storage, we will get much more compression and cheaper storage with Redshift or other technologies, right? But then, we do want to do analytics, and we want to use the data, not just store them for backup or archival purposes. We want to actually use them nightly for the analytics. So that's where the column store provides a good balance of providing us 7x compression, and at the same time be as real time as it can be for disk access.
Right. So what technologies are you using for the machine learning?
We use like the Keras, TensorFlow, and the standard toolkits like it.
Okay. Is it a Python stack then with?
Yeah, pretty much Python stack. We kind of standardized on a Python stack so that it's much easier to build and reuse tools rather than separating it into so many forks. Yeah.
So your Python stack in the MLOps is going directly against the MemSQL database from
Yes.
Python connectors.
Yes. Yep.
And that's a daily continuous training phase happening along with your transactional ingestion and analytic queries, serving API calls, ingesting from the MQTT tier.
Yeah, it's all in the same cluster.
Terrific. That's great. Well, Jay, this has been a fascinating conversation. I really appreciate your time today and your willingness to share your experience with the MemSQL community. It's Infiswift Technologies is fascinating in terms of what you've put together for an industrial IoT platform with AI in these different use cases for oil and gas and solar, renewables, energy, et cetera. What's your next step for the platform for Infiswift Technologies, and your next step with using MemSQL?
Yes, first of all, thanks to MemSQL team for putting together such a brilliant product. Given my background in distributed systems, I know what it takes to build a solid product like MemSQL. So it's really well thought out product. So that's why I love it. And personally, I made a bet on MemSQL like 4 years back, and I can see how it has served us so well now. So the next steps for us are like essentially scaling. So we are at a kind of a inflection point where we are generating a lot more leads. We are still a startup, 4 years old, but we are generating a lot more leads and a lot more demand for the data, and so more use cases. And in fact, now one of our customers is in Japan, so we are planning to do a second installation of our production cluster in Japan, because some of the local laws require the data to not leave Japan for some of the scenarios we are working on. So scaling both in terms of bringing up another cluster as well as onboarding more customers onto our clusters, and then serving more analytics and AI applications. So really looking forward for that.
That's fantastic. Well, we look forward to seeing the continued success of you and the team at Infiswift Technologies. And thanks again for the time.
Thank you, Dominic. I really enjoyed the conversation. Thank you to all the audience as well.
Take care.